So the rod has been bent into a semicircle and has charge density lambda. Can we kind of all agree that the length of the bar is going to be pi times r, like the entire length of the bar? So is it too big a stretch to kind of put over here on the side that the total charge of the bar is going to be lambda times pi r? Is that too big a stretch? Does anybody need that explained? Lambda is defined as the charge density, which is the charge per unit length. And that's what density is. It's a linear charge density, so that's why I put it in terms of length. Remember, there are 3 different kinds of symbols to use for density. There's lambda for linear charge density, sigma for surface density, and rho for volume density. This one is clearly, I think, falls in the category of a charge per unit length, and they even tell us to use the symbol lambda. So if I wanted its total charge, I would take the density and multiply by the total length. Is that okay, David? So with that said, I'm just tucking these off to the side for a minute because I think they're going to come up. I'm going to have lambda in my answer, and I can have r in my answer, and pi is a constant. I can have it in my answer. All right, so I've identified dq. The first thing we want to do is try and identify a way of dealing with dq. It's how much charge is there. And again, by definition, we could say dq is to ds as we could say q is to the total length, but we can't have q in our answer. So that'd be the wrong way to go. On the other hand, we could just use the fact that this has to equal lambda, charge per unit length. That is a density. So I could write this as dq equals lambda ds, or as we talked about before, dq is lambda r d theta. I would have to find a way to measure theta though, and I'd want to use a reasonable way to measure theta. So looking at this, I'm kind of expecting that if I draw a line from dq to my charge, that suggests a force, or dq to point O, that suggests there'll be a electric field in this direction. Does that make sense to you guys? I'm not saying contribution to the force anymore because we've talked about electric field, so I'm going to do what the problem asks, which is talk about contribution to the electric field. So I will write this as dE, my contribution to the electric field. I am also noticing a certain amount of symmetry. Are you guys also seeing that there is symmetry here? So I think there will also be a contribution to the electric field that is downwards and to the left that will be of equal size and magnitude, well, equal size and direction. Is that all okay? So I'm going to anticipate a direction for my answer that is straight downwards. Let's do better. Like that? Is that all okay? So I am interested in this angle, which I'll call theta, and I think that I will set this to be 0, and this will also be theta. So when I talk about pointing to this charge, although I've covered this, so let me see if I can rewrite this so we can see it. I think dq will be lambda r d theta, where this theta and this theta are the same. Is that all okay? So I think that's the answer to question A. I'll use that as my dq. Any questions? All right, portion B. Indicate on the diagram above the direction of the electric field at point O. I've already done that. I think it's going to be along the blue arrow. Is that all okay with you guys? All right. C, using your DQ from A, what would be the most useful limits of integration for calculating electric field at A? I would say that we can either go from negative pi halves to positive pi halves, or we could do 0 to pi halves and multiply by 2. So those would be, I think, the best limits to use. 2, what could you do to use symmetry to simplify the limits of integration? I think I just answered that. Are we good to go? Can I keep walking down this road? All right, so 3, if able, I am able. What would be the expression for the magnitude of the electric field? All right, let's go ahead and build the whole thing. Now, I'm going to take a little bit of time here to remind us that we're working from Coulomb's law. But what we're looking for specifically is the electric field. So if lowercase q is the point charge, or if big Q is the point charge, I don't know which one you want to be the point charge or the test charge, we're going to say that our electric field contribution will be whatever this is divided out by one of the charges, the charge that we would have placed here as our test charge. So either way, I'm going to write this as dqk over r squared. That's where I'm going to start. That all okay? Any question about where I came up with that or why? I'm just using the definition of electric field as being force divided by test charge. So with that in mind, I'm going to build my integral from what I have here already. I'm going to replace dq with what I solved, lambda r d theta k. R squared is going to be capital R squared to match up with the symbology given to us. And it looks like every single piece of charge is the same distance away, capital R. And now I'm going to realize that I probably don't want dE. I probably want dE in the y direction, which is going to be dE. Which one should I use, cosine or sine here? Cosine, yeah. If this is where theta is, I want this component, that's the adjacent component, okay? So cosine theta, which will be dE in the y direction equals lambda r d theta k over r squared cosine theta. All right, that's putting it all together. That's not actually doing the work, it's just putting it all together. We still have to do the work. So, the work. Take anything that doesn't change with theta and separate it from everything that does change with theta. So, does lambda change with theta?
No.
Does r change with theta?
No.
Does k change with theta? Does cosine change with theta?
Yes.
Does r squared change with theta?
No.
Put my d theta over here. Integrate both sides. And set appropriate limits. Can I keep going, or any troubles? All right. I'm going to cancel the 1r, so 2 lambda k over r times the antiderivative of cosine of sine, evaluated from 0 to pi over 2. Putting in my top limit, what's sine of pi over 2? 1. Subtracting sine of 0?
0.
That would be electric field. Do you find it weird that there's not an r squared in the denominator, like the units don't seem right? Things to pay attention to. If you feel like the units don't seem right, remember lambda is probably going to be the total charge divided by pi r. Because we're in lambda, we have it in terms of lambda. Lambda is coulombs per meter. And then I have meters in the denominator, so I still have my meters squared. It's still there. It's just that it's buried in the lambda this time. That's it. I already have an expression for the force, correct? So let me see if I can remember it straight from memory. It's, are they both Q? So, no, Q1 and Q2. Are they equal? All right, so Q1, Q2, K over d squared plus z squared to the 3/2 power with a z on top? Yeah. Is that what you get? I'm not deriving it, but we did this one in class, right? So is that okay to start from there? You guys are all right with that? Do you have Desmos or a calculator?
Yeah.
Well, let's grab our calculator. Anytime you're asked, yeah.
Should it be 2 times that?
Should it be what?
2 times that, sorry.
Okay. So 2 times where?
Just the whole thing.
Okay. I'll take your word on it. So you have access to your calculator, right? Anything that's a constant there, put in a 1. So for your y equals, if you want the shape of this graph, it looks to me like you would just have x over 1 plus x squared to the 3/2. Try putting that in for your y equals. And then zoom standard or zoom whatever. Now, while you're doing that, you guys who are clearly not doing it around me, which is a whole bunch of you, either because you don't want to or don't think it's a valuable experience, or you don't have a calculator, which I find to be probably laughable, you're going to be faced with doing this. There's a 90% certainty that on the exam you'll be required to sketch a graph, and probably more than just that. You'll probably have to do more of plotting rather than sketching. It is every single exam so far since the dawn of the AP exam has almost always had a part where you've had to sketch the shape of the electric potential or the electric field, and they are generally attempting to trick you each time. They're going to try and provide some kind of trick. This one is actually as straightforward as I can provide it because there's no discontinuity. That's not going to be the case for the very likely examples. You'll have examples that will have weird things in them that will create odd discontinuities in the graph. This one's nice and continuous. So if you look at this one closely, you realize that when x is small compared to d, it's linear. Are you guys listening to what I'm trying to say? So when x is small compared to d, it's going to be a linear function because the bottom's not going to change very much, but the top has just an x in it. So my graph is going to start out linear. But I also know that in the long run, when x is big compared to d, it dominates the bottom. And I just get x squared in the denominator. So I know that at the end, it's going to do something like that. I would probably assume that it peaks somewhere in there and then decays. There's a point where the force is at a maximum. In fact, you guys should be able to figure out where the maximum is. Where is the point that would have the maximum amount of force? This is force versus position. Now, you guys who have had a little bit of even pre-calculus know how, or yeah, you guys call it pre-calculus, have known how to do stuff to find where the maximums and minimums of functions are. But if you've had calculus AB, you know that just finding the derivative of this function, you could figure out where the maximum and minimums are. There's going to be a clear maximum, a point where the slope is 0. Now, plotting on your calculator gives you a reasonable chance to see what the shape of these functions are. Don't take this for granted. If there's going to be a sketch of a graph on your test, it's probably going to be 3 to 5 points out of 15 on your FRQ. Usually it's worth a lot of points. So, yeah, I want you to be able to do this. And I want you to be able to talk it out. And you need to be able to look at limits. So always look at X when it's small and X when it's large to give you an idea of what's happening in the middle.